we'll talk about allocators part 2. So again, this is kernel memory allocators. General purpose user space allocators have certain issues that they have to manage, primarily centering around fragmentation, and also driven by the fact that they are general purpose allocators. Like they have to support arbitrary memory sizes, applications doing whatever they want with memory. Maybe the application uses an object pool, maybe it doesn't. So we have all of that kind of flexibility that user space allocators have to deal with. Kernel allocators have a slightly different set of concerns. They have to be efficient. They have to deal with fragmentation. They do need to be sensitive to fragmentation, but they run longer than any other piece of software in this system. But they also have some simplifications. Okay, so we started talking about these allocators. Resource map, which is just kind of like the CS24 style allocator. Power of 2 free lists. McCusick Carols, which again was a power of 2 allocator, but it would use individual pages or runs of pages as necessary. And then binary buddy allocator. So these are all sort of very simple approaches. Basically, you have this characteristic that internal fragmentation is huge because we tend to round everything up to the next power of 2. And that isn't great. So we waste a lot of memory with these kinds of allocators. But they do tend to be fast, particularly for deallocation, coalescing, and they tend to be really fast for finding a chunk of memory the appropriate size. Okay, so power of 2 free list wasn't great. Remember, we used a bit of the blocks to tell what size the block is, and resource map allocator we just don't even really care about in kernel space. So these were some of the characteristics of these allocators. Today what we're going to talk about is a completely different approach to memory management in the kernel, which is what most real OS kernels do now. So first thing is that we haven't talked about virtual memory. Virtual memory is actually really important in operating system kernels. So we need an allocator that's virtual memory aware. And so that's one of the things we're going to talk about. Infrequently, it's frustrating to me because sometimes when you read discussions of memory allocators, they'll say that the pages need to be physically contiguous. Well, user space doesn't care. And we'll talk about that a lot as we get into virtual memory. I think it's actually the next topic we're going to discuss. And virtual memory systems make it completely irrelevant whether or not virtual memory is physically contiguous or not. The mapping does not care. But the thing is, the kernel does care sometimes because we may be interacting with devices, and devices care a great deal about whether or not memory is physically contiguous. Okay, so this is what I was saying before. User process may see a virtually contiguous region of memory. That's all it really cares. The memory management unit takes care of the virtual to physical mappings. It just really is indifferent. Okay, so here's the reasons why we care about physically contiguous mappings. One is if it simplifies the memory mapping that the kernel has to manage. You're starting to see a little bit of this in Project 4, where it talks a little bit about user space memory mapping, kernel space memory mapping. This is something that you're starting to have to be aware of. I haven't spent much time talking about it because thankfully it's not super critical for Project 4. But in Project 5, I'm going to have a special lecture where I go through and tell you exactly how Pintos manages memory, virtual memory, and lays it all out so that it's easy to understand, so that you can see what you have to build for Project 5. That's been one of the biggest challenges of that project, is simply knowing how Pintos works and where to start. Okay? But if we have a simple virtual to physical mapping, then it becomes easier for the kernel to manage it, and it can be more targeted with TLB flushes. Okay? So if I need to, like I say, every time the page table changes, I have to flush translation look-aside buffers because the translation is no longer accurate. Okay, so that's the detail here. But the kernel does do certain things to set aside a pool of frames for itself to use, and it maps those to virtual pages. And so if it can keep that mapping simpler, then I don't have to change the page table as much, or at least that portion of the page table. Okay? So that helps reduce the overhead of the virtual memory management within the kernel. So that's one thing, but nobody really cares very much about this, I don't think. But the second reason is actually the one that's really critical. Okay? Again, if you took CS24, you probably recognize this picture. This is kind of what the machine layout looks like. You've got the processor, which actually does instruction execution. You've got the memory management unit, which does virtual to physical address translation for the program. Okay? But the program lives in main memory. And the peripherals, obviously, all live outside of that address translation mechanism as well. Okay? And we do want to use direct memory addressing as much as possible. So remember, DMA is really about a peripheral becoming a bus driver. So the CPU might tell the disk controller, I want to do something. I want to transfer these blocks of data from the disk to memory. And the problem is that's really slow, so we don't want the CPU to babysit that. So the CPU will talk to the controller and say, this is what I need you to carry out. Then the peripheral goes ahead and does it directly. And so if you have a modern bus, like if I remember correctly, the old ISA bus, which thankfully probably none of you know about because it's way before your time. But that was like our PCXTs, ATs, those kinds of computers used an ISA bus. And that was industry standard architecture, not ISA instruction set architecture. So it's an overlapping acronym. But PCI buses support multiple bus masters. So you can have something like the graphics controller or the display controller say, I want to write data to memory, and the bus supports it. Okay? So that's cool. That's a step forward, I suppose. And then, of course, the last step is once the operation's completed, then the peripheral can signal to the processor that it's done. Okay? And this is where things like the I/O APIC, I keep ranting about the I/O APIC. Well, it's got some number of interrupts available for peripherals to signal on, and the OS will set that up, like who maps to what interrupts, and then it can just fire an interrupt, and then the processor knows the operation is completed. So that's nice and clean. Okay? So the question to ask is, what addresses or what address space is the peripheral in when it's interacting with main memory? Okay? And the answer is almost clear from the picture, which is that the peripheral clearly lives outside the MMU. That's the first obvious thing. So is there address translation going on? Well, the answer is definitely not from the MMU. There is a new kind of technology which is in use by an increasing number of peripherals called IOMMU. So now peripherals can actually have some capability of doing address translation as well, but it still tends to be that peripherals prefer an address range, a specific address range of the physical address space, and you can change it a little bit, but not a lot. And so typically that imposes constraints on how the kernel interacts with these peripherals. Okay. Now, so I say here they frequently use physical addresses. Again, this may be a little bit of a misstatement nowadays because we're definitely moving in a direction where they have their own kind of virtual addressing mechanism. But it definitely lives outside the processor's virtual memory addressing mechanism. Okay? So because of that, DMA transfers, if we are transferring to a region of memory that the kernel is set up to receive a disk buffer or to write a disk buffer out to the peripheral, things like that, typically the kernel needs to be sensitive to these kinds of constraints. Okay? And so what you end up with is a kernel allocator that has to say, yes, you need a physically contiguous region of memory, and maybe even say it needs to be in this physical address range. Okay? So those are the kinds of things that kernel allocators need to think about. And like I said, this is sort of the most constraining issue when it comes to the way these allocators work. Okay, enough about that. Now, I'll just give you the punchline because I talk about this toward the end of the lecture. But binary buddy allocators are really good for managing pages. And so that tends to be what happens. Binary buddy allocators can be used to say, I need a physically contiguous region of 4 pages. Or I need a physically contiguous region of 64 pages, and then I'm going to use that for doing disk transfers. Okay? So you'll see multiple levels of allocators working in a kernel. You'll have a page level allocator that maybe does that, and then within those pages we'll have other allocators. So now we're going to talk about those. And the wave of the present, it's been around for quite a while, but basically the cool, nifty way that everybody does object allocation in kernels is using caches of objects. And part of the reason why is because kernels tend to be limited chunks of code, and so they have a limited number of object types that they tend to work with. You have your file descriptor structs, you've got your thread structs, you've got a few common things like that, maybe synchronization structs, but there aren't like a billion different kinds of types that the kernel uses. I mean, it's a fixed piece of code. And this is another distinction between kernel allocators and user space allocators. They don't have any idea what the user application is going to want to do. So the idea is grab a chunk of memory for a particular object type, and then use that whole chunk of memory for allocations of that type of object. Okay, remember that one of the common patterns is allocate, free, reallocate. So basically what we're doing is building an object pool. And the neat thing about that is typically these things are going to be word aligned. So the whole struct size is going to be some multiple of word size. Okay? And so we can pack a whole bunch of these into a single region of memory. So internal fragmentation goes away. And since we always allocate and release the same kind of object in the same regions of memory, external fragmentation goes away as well. So we basically wipe out all of our problems with fragmentation by using pooled object allocators. They have a number of names. So we have object caches, pooled object allocators. You'll see a few other names for them as well. Okay. So, allocations and releases tend to be constant time. You can't get much better than that. And even furthermore, these allocations and releases tend to be just a few instructions. Because it'll tend to be look up the next object that's available, or the space for the next object in the pool, and then update the pointer to point to the next free object. And so it might be a handful of instructions very, very fast. So cool. I love that. Okay. Another interesting thing. Cache utilization. If you think about a power of 2 free list, or any kind of power of 2 allocator, you end up with a lot of chunks of memory aligned on powers of 2 addresses. And that causes havoc for many caches, because remember that most caches are not fully associative. They tend to be set associative, maybe 4-way, maybe 8-way set associative. And a great way of causing problems is having a sequence of addresses that all map to the same cache set, or the same small number of cache sets. Because now the cache looks like it's cache set size as opposed to the full cache size. And so you end up with situations where you get conflict misses. You generate a lot of conflict misses with power of 2 free list allocators. Okay? So that's a big issue. Okay? It dramatically increases the likelihood that you'll have multiple, I say here map to the same cache line, but really the issue is with cache sets, because nowadays processors will have 4 or 8, or if you're lucky, 16 lines per set, and so that'll reduce the potential for thrashing your cache, but still happens pretty frequently. And again, this problem just disappears as long as your objects are not a power of 2 in size. If they're a power of 2 in size, you still have problems, but there's other strategies for dealing with that. But a lot of times they're not, and so just packing them into a big chunk of memory, minimizes that issue, because now you have various memory accesses, and they're not all going to be power of 2 addresses. Okay, so that's nice. That's a side benefit, and you will actually see this mentioned in research literature. Okay, I'm going to talk about 2 cached object allocators. First one is the zone allocator, and I'm slightly sad I don't see any Macs right now. The only Mac is mine. The reason why is because OS X actually uses a zone allocator, and you can print out the list of memory zones and their memory utilization from the command line. So that's kind of a fun little thing that you can see. But yeah, the zone allocator is basically page level garbage collector because we would like to reclaim virtual memory pages as they become available. And so zones basically are regions of memory that are for a specific object type. Okay? So you'll have the semaphore zone, and you'll have the file descriptor object zone, and things like that. Okay. So yeah, I have a whole list here: process and thread control blocks, virtual memory map objects, various other details. It turns out that there's a zone of zones as well. So if you have a zone allocator and you have to describe zones, why not have object cache for zone objects as well? Okay, and so this is why I'm sad that there's no Macs in the audience, because you could do sudo zprint and you would see the list of zones that are currently in use by your operating system. Okay, so zones are caches, like I was saying. There is a zone structure that records various details about each zone. And this is not complete. The zone struct is actually quite large. So you have the name of the zone, and it's a string, so it's actually easy to understand if you're a human being trying to understand what the kernel is doing. So you have the size of the element, so what size are the objects that I'm storing in this zone? Also, what is the current size of it? How large is it allowed to get before you should start failing allocation requests? And also, how much to grow the zone. Okay. And you'll notice, like I say here, all of these are multiples of virtual memory pages. Okay. Now, objects that are in use in the zone, so we'll talk a little bit about that. Remember that there is a garbage collection component to this. And the zones themselves, you can see the very last member is next zone, so that allows you to chain these zones together. Okay. Now, this maintains a free list, and it's very similar to the way that any kind of good allocator works. If I chain together all of the free objects, or the spaces where I could stick free objects, then allocation becomes a constant time operation. What's the next object I can return? Well, whatever. Do I have it in this picture? I don't have it in the picture. That's the one that makes me sad. Wait, is there a free? Yeah, no, it's free elements. I don't know why I missed that. But free elements is just the first object in this list of available spaces that you would use. So you would just return that pointer, but before you do a lookup saying, hey, update free elements to point to the next one. So again, that's just a few instructions. And off you go. So allocation is super fast with this approach. Okay, so zones have virtual pages associated with them. This is how we keep track, and I think that is, if I'm not mistaken, that is definitely not represented in this picture. But we have virtual pages associated with it. And so let's say that we need to grow a zone because we need more objects of a particular type. So the first thing that the zone allocator does is it talks to the pager, gets a chunk of virtual memory, so some integer number of pages. And then, like I say here, the typical size, like the desired size, will be alloc size. That's the size, that's the number of pages it would like to grow the zone by. Now, if there's no way of satisfying that request for some reason, then it'll take the element size and just round it up to some whole number of pages. Okay? And then try to do that. So this is if the OS is in really severe low memory conditions. But in general, it'll allocate a number of blocks that are the size of alloc size. Okay, so it's got this chunk of available memory now. So what it does next is it chops it up. It chops it into a bunch of objects, or object-sized chunks. So that's neat. That's straightforward. Now you'll notice some interesting little nuances here. First of all, I've got 3 pages, but the objects may span from one page to the next page. So end of one page to the beginning of the next page. No biggie. Okay? Also, you may notice that we may waste a little bit at the end. But if we have a large number of pages, the waste should be small. It's always going to just be some, fraction of element size. It shouldn't be a whole element size because that wouldn't make any sense, but it's going to be something less than element size. Okay. Then all of these elements are linked together into a free list because they're all available spaces for an object to occupy. So hopefully you can see how that makes it really easy to do allocations. Okay? Now, this can be done as often as you need until you have a ton of places to put new objects. When you allocate an object, just like I was saying before, Zalloc or Zalloc is the way of doing this. And just an interesting little detail here, zone T, I can't remember if it's just a pointer to the zone struct or not. I'd have to go look that up in code. But the neat thing about it is those zone types can be looked up by various kernel subsystems because they know what kinds of objects they're going to be working with. The file system code can look up the file descriptor zone, and they can look up other like disk block zones and things like that so that it's easy to access them. So you're not looking up zones all the time. That's not going to be overhead. And part of the reason why I mentioned that is because you'd have to do a linear search through these, the way that it's currently described. Okay? But Zalloc is how you allocate an object of a particular type. Okay? And of course, if there's no free elements, then it'll grow the size. And then we just do a simple pointer update. You know, free elements is the value that Zalloc returns, but we update free elements as necessary. Okay? So easy. This is pretty cool. All right, so garbage collection. The way that this works is the zone allocator keeps track of details for each virtual page that's part of the zone. Okay? And by part of the zone, I mean part of the object pool part of the zone. Okay? So we have these details. Alloc count, collect count, and next, so that we can string these things together. So alloc count is just set to how many objects live either partially or completely within this virtual page. And so you can see the way that my picture is drawn, that each one of these, 1, 2, 3, 4, 5, 6. Yeah, the way that this is drawn is that every page has portions of 6 objects in the page. Okay? So even though the last object in the first page is just like 1/3 in that section, well, it's still in that section, so it's included there. Okay? So garbage collector has to do a traversal. This is kind of a lame reality of these things, although you'll notice that the emptier the page, the emptier the object pool, the happier it gets because the less work it has to do. But it goes ahead and traverses all these things, all these little descriptions of pages, and it sets all the collect counts to 0. Okay? Next thing it does is it walks through the free elements list. Okay? It knows how big element size is. It can go ahead and start with free elements and walk through the whole list. And basically, every time it lands in a virtual page, it increments the corresponding collect count. Okay? It's easy enough, okay? Because it knows that that's an available object. If once it's completed, it can go through and look at all these little descriptors again. And if it finds pages where alloc count and collect count are the same, it can reclaim that page. Okay. Now, there's obviously some subtleties here, because if you have a page that can be reclaimed, like imagine the middle page was going to be reclaimed. There were some objects in the first page and there's objects in the third page. The middle page can be reclaimed. Well, the problem is it needs to make sure that any pointers into the middle page stop doing that. So you have various linked list updates that have to occur if you're going to manage these data structures correctly. So this is one of the things about systems that I think makes it challenging to teach and challenging to learn, is you can describe a concept like this and you can say, oh, this is great, this is easy. But then that's a giant problem hiding in there that you wouldn't realize unless you tried to implement this. So updating the free elements list can be a little bit challenging. Nonetheless, I think it's probably straightforward to solve. Okay, so we go through second sweep and find pages that are available, and then they will be queued up to be freed. Okay. Now here's the thing. You may notice that we set up this nice clean memory pool, this nice clean object pool, and if it's brand new, which pages can we reclaim? All of them, right? So we have another issue here that we need to make sure that if we allocate a chunk of memory for an object pool, that we don't free it right away and just waste all the effort that we put in. Okay, so that's another one of those challenges that you have to resolve when you have these kinds of systems. But you can notice that the pager is what triggers this garbage collection pass, and it works pretty straightforward. Okay, so this is just describing the zone of every kind of object. Now, you will notice sometimes when you're writing a program, you don't necessarily want a pointer to an object. I just want 16 bytes. I just want 64 bytes. I need to do something in 64 bytes. And so you say, I want a buffer, and you use it, and then you finish with it. Well, so the zone allocator actually keeps zones for those kinds of things as well. Okay? So if you have situations where I need a buffer to load some data or store some data, the zone allocator can service those kinds of requests as well. Okay? So that's definitely a useful thing to have in these kinds of systems. So now you can fold all allocation requests under this one unified kernel allocation system. Okay, does it make sense? Pretty neat. There's a lot of cool characteristics here. Allocation, super fast, right? We have very little issue with fragmentation, both internal and external fragmentation, so that's great. And we can do allocate, free, reallocate really fast as well, right? Because we just, when we free, just put it on the front of the free list. That's always the solution. Just put it on the front, because that's going to be the fastest thing to update. And so we can handle allocate, free, reallocate super easily. If there are issues, which there aren't any very serious issues, the fact that OS X actually uses this allocator all the time for its kernel should indicate that there are very minor issues, if any at all. So basically it involves garbage collection. If you have a low memory scenario, how does the OS respond in that kind of a scenario? Okay, so that's an important detail here. It does add a little bit of overhead, but that's not a big deal. Okay. I should say I've been using a Mac for a long time, and I've never gotten really grumpy because the zone allocator is misbehaving. Okay. All right, so that's the first kind of allocator. Was there any questions about zones at all? All right, now you'll notice that the second kind of allocator is very similar. Very similar concept. That's a bit of water. So slab allocators are just a slightly different implementation. Basically, a slab is a contiguous sequence of virtual memory pages. So you can see in your zones when you had this list of virtual pages that those little virtual page chunks are the slabs, basically. But you have each slab sort of describing its contents. And so that's kind of the difference here, is that when you have the chunk of virtual pages, there's not something that necessarily is separate pointing to it. The slab is the space for allocation plus some descriptive information. Okay, so you have a cache that holds objects of a certain type, and so you'll have a cache for each kind of object that the kernel might want to allocate. And then these slabs are in caches. Okay, so to talk about this, here is a somewhat helpful picture of what's going on inside. And so you can see that there's slab level details at the top. You pointer to the list of the other slabs in the cache, so I need to be able to string together the slabs in case a particular slab is full. Now you'll notice another important detail is that slab will be potentially empty, potentially partially full, potentially completely full. Okay? And a lot of times it makes sense to actually manage slabs in a cache based on this slab is full, this slab is part full, this slab is completely empty. So you'll see that kind of thing in a slab allocator as well. Okay, let's see. Pointer to first object in the slab. So that was cache level details, and then we have slab level details. So basically, in the slab, where's the first free object? And then there's some chain within the slab of all the objects within the slab. And so that's one difference between slab allocators and zone allocators, is that these chunks of virtual memory pages in the zone allocator could be strung together, but in a slab allocator, each slab is kind of a distinct unit. And that does make certain operations easier. You can allocate and release slabs on a per slab basis, so that helps. Okay, objects have their own descriptors. So you'll notice in the picture on the far right that sort of the orangish stuff at the bottom, those are the actual spaces for the objects themselves. Okay? But then objects also have an array of descriptors that describe the various, basically the status of the various objects in the slab. Okay? The main detail that the object descriptors have is who's the next available object. If the object is in use, then it'll say I'm in use. Otherwise, it'll have information about the next available object in the slab. So again, you maintain this free list. It makes it really easy to do allocations against the slab. All right. Like I said, that picture is mostly useful. There are definitely details that are left out of it that increase its confusion level. So, but it's kind of a complicated data structure, so I didn't want to try to cram too much onto one slide. Okay. So you have this reality that you have some number of virtual pages being used for this, and the cache level details, the slab level details, and the object level details do consume space within this slab. And so sometimes you'll see slabs that factor out the object description. Okay. Now, you kind of end up with this weird thing. And it's a little bit confusing. Like I say, external slab descriptors have their own object cache, so they have a object cache is the right term for it in slab allocator. So it'll have a sequence of slabs for managing slab descriptors. When they're inside the slab, they'll be simpler, so they take up less space. Okay. And so the way that this works is that depending on the size of the objects being stored in the slab, the allocator may say, you know what, I need to factor out the slab descriptors, the object descriptors, so that I have more space to devote to objects themselves. That's the idea. Okay? So large objects, it'll say, well, I could only cram 8 of these per virtual page. I might have 4 pages. So why don't I go ahead and factor out the object description so that I can make sure I don't lose too much space to the large objects. To the descriptors. I need to make sure I keep that straight. Okay? So that's the idea. And so here is an example of large objects. Okay? So we factor out the descriptor information. We're expecting that this isn't going to be too bad. And then those things point to the actual chunk of virtual pages with the objects. And because they're relatively large, we want to have the virtual pages devoted solely to them. Okay. All right. Let's see. What else do I need to describe for this? Yeah. So yeah, this is basically just what I was describing. You can see there's some benefits in treating small objects and large objects slightly differently. Okay. It's not really rocket science. Okay, let's see. Yeah, so this is the other interesting nuance, and this is one of the things that can be a little bit confusing. So let me go back and show you. Large objects, we don't want to lose a lot of space to internal fragmentation, so we factor out the descriptors. That makes sense. But the problem is if you can fit a lot of objects into a slab, it seems wasteful to have the descriptors and the objects separate. And so those two things get folded together for small objects. Okay? Like it says here, the object descriptor table would consume a lot of space. So why don't we just use free objects themselves to hold the descriptors? Okay? So that's the idea behind how we optimize space in a slab allocator. Okay? So now what we're saying is, the descriptor section is gone because it's actually inside the I'm not in use, but inside the free objects. Change them together directly. Okay. Let's see. There are often slabs for, or I should say object caches, that's really the correct term, for doing small specific size allocations, typically power of 2 allocations. They would pack really well into a slab, so that's great. You can have object caches devoted to DMA-friendly buffers, ones that are DMA indifferent or intentionally not for DMA, in case there's other parts of the kernel, like message passing would be a great example between processes, would be a great thing to say, I should not use a DMA-friendly buffer because those should be for the disk level code and so forth. Okay, and so this is an example of what the Linux slab allocator does. Okay, pretty straightforward. Oh yeah, so I want to ask, are there any questions so far? But you see how it's the same idea, right? As the zone allocator, it's just a pool of objects or pool of available objects, and free lists are totally your friend. They make everything fast. And then we are doing all this on the virtual page level. So the kernel allocator is very aware of virtual memory. And that makes it much better to use inside the kernel where that is a real consideration. The user space, who cares? But in the kernel, we care a lot. So this is a nice approach. All right? Last thing, slabs are interesting. We talked about the zone allocator, and you remember that each virtual page, like you have objects, you're packing them in, and they're all like kind of weird different addresses, and that's okay. That doesn't cause too much of an issue. But if you have a few large slabs for a particular object type, you can end up with a situation like this. Okay? Notice you have a couple slabs, one kind of object cache, and notice where the objects start. Well, they all start at similar offsets from the start of their virtual page regions. And if this is built against something like a buddy allocator for managing virtual pages, then it's very likely that these slabs will occupy a power of 2 number of virtual pages. And then these offsets could easily cause thrashing. If you have a cache and you're trying to traverse these objects, and you're getting a lot of accesses that can correspond to the same cache set. Okay, so this is one of the performance issues that they ran into. Now I would say that it was probably in the 70s and the 80s that they ran into this, when you had more direct map caches and caches with low amount of associativity. Okay? Now that we have caches with a lot higher associativity, you don't run into this nearly as much. But there's a really clever little solution. Okay, so I talked about that. Slabs addresses start with power of 2 boundaries, so that tends to be a problem. So conflict misses. So there is a technique called slab coloring, and basically what it involves is offsetting the start of the objects in each slab by just some little amount. And you vary this across different slabs in the cache, and that becomes the slab's color. So you have and it's weird because the color is a number, it's not a real color. But this slab's color is 0. This slab's color is 8. This slab's color is 16. And that causes all the objects to be shifted slightly within the slab. Okay? So we do something like this. Remember that since we're trying to fit a fixed size object into a fixed size slab, and the two numbers may not be evenly divisible, we may have some space left over at the end. So instead of having all that space at the end of the slab, why not move a little bit to the front and offset those pointers? Okay, and so you can end up with something that's a lot more cache friendly. And so typically the way that these slab allocators work is that they'll have a minimum and a maximum slab color like my color is 0, my color is 48, or my max color is 48, and then the actual increment as I allocate various slabs for the cache. And it allows you to make sure that the objects that you hand out are still appropriately aligned for the machine architecture. We want that to be fast, but it's going to be a lot friendlier to caches with a lower set associativity. Okay, does that make sense? I think this is like one of the coolest things. I've never been able to figure out how to incorporate this into a CS24 final, so that's probably a good thing. But it's just a really clever little technique to try to mitigate conflict misses in hardware caches. And it's funny to me because at this level, we care about that kind of stuff. This is used by everybody, so the faster we can make it, the better. Okay? Let's see. So Linux, yeah, started to use it. I haven't looked to see what it currently uses, whether it uses a slab allocator currently. But it's been doing this for a really long time. And the challenge, and I've mentioned this already, so you already know the punchline. But the challenge is if you're managing virtual pages using a page allocator, using similar techniques as we've talked about, like a resource list allocator or whatever you would call the CS24 style allocator, where you're just saying, okay, you can have 5 pages, you can have 9 pages. When you're done, give them back. The problem is over time, no matter whether you're using first fit or best fit, you're going to end up with fragmentation. But now it's happening at the page level versus at the individual byte level within the address space. So that can be difficult, and since we do care about physical adjacency for certain things like DMA transfers and so forth, the kernel needs to take care that when it allocates virtual pages, it can maintain physically contiguous runs of them. And so that's why the buddy allocator actually works really well for this. You want 1 page? Great. You want 16 pages? No problem. It can make sure that it hands out runs of pages that are physically contiguous, as well as virtually contiguous, if you will. Okay? So you have a binary buddy allocator for the page allocator. Okay? And then that is utilized by the slab allocator. The slab allocator can divide these runs of pages into caches, and then each slab can be chopped up into objects, and it becomes relatively straightforward to do that. And over time, when a slab gets reclaimed, it can be turned back into the buddy allocator. That's the page level allocator. And it can just, chunk stuff back together as needed. So you end up with a system that's able to maintain physically contiguous runs relatively easily. Okay? So that's the idea. Let me see. Slab at each cache. Okay, so that's also interesting. The slabs are all being the same size. So that also probably simplifies the memory management for the buddy allocator. So that you don't end up with, how would you call it? I think that would be internal fragmentation if you're not able to satisfy allocation requests just because of placement constraints. Okay. So that will help as well. Okay, any questions about any of this? All right, I believe that's the end of this. Let me double check. Oh, I do have a few more things. Oh, yeah, this is the last little detail that I think is useful to know about. We do have time. Yeah, we just have a little bit more time. So, like I mentioned, it is useful to keep track of when slabs are full, empty, or partially full. Because, obviously, if you have a new allocation request come in, don't consider full slabs. Why even would I consider full slabs? But if I have a choice between an empty slab and a partially full slab, which one should I choose? It would make the most sense to satisfy an allocation request against a partially full slab so that if something needs to be reclaimed because I'm running out of pages, I can just reclaim an entire slab. So it makes sense to use partial slabs when I'm satisfying requests. Okay? And so basically, the slab allocator maintains distinct collections of these slabs for each cache so that it's easier to know where to look so that, again, I can be virtual memory aware. I can keep empty slabs empty as long as possible so that if it needs to be reclaimed, that's not a problem. Okay? All right. Now let me double check. Yeah, so that is the end. What we're going to do next time, and I think we're going to do this on Friday, is we'll start talking about virtual memory. And I realize that that's early because the virtual memory lab is not up yet, but we have a lot to talk about. I think I mentioned this pretty much every time I teach CS124. Virtual memory is the hardest part of this class, and it's mainly because there's a lot of abstractions worrying about, and it's just difficult to keep track of everything going on. File systems are not as hard because of that. They're hard because file systems just suck, and because you want to achieve a high level of concurrency. So that's why the file system lab sucks. But virtual memory, I want to make sure we spend a good amount of time talking about the abstractions, and especially the Pintos abstractions, because any OS can pick any way it wants to do this stuff. So I want to make sure you're all fully armed before you walk into that lab. So we'll start picking that up on Friday. So see you then.